Hey folks, welcome to Online Notes with Mrs. Kavicki. We are going to use this as a supplement because I'm going to be gone a day, so I'm including these for you guys so we can still get through the material I want to get through. All right, we're picking up in our notes. We're in chapter 3, scientific measurement, and hopefully if we got through what I planned to get through, we should be on to number 5. We already talked about length, mass, density, volume, and now we're picking up with temperature. Good to go. There you go. 3 temperature scales that we're going to need to get good at. Celsius and Fahrenheit we should be already pretty familiar with, and Kelvin is maybe the new one. That's the one scientists use very often. Here we have temperature that water freezes in this first column, and then temperature that water boils. Celsius is nice, easy to remember, based on based on water. 0 degrees freeze, 100 degrees boil. Fahrenheit, not as easy. Okay. Kelvin might not seem as easy, but it is nice because it's on the same scale as Kelvin. That means 1 degree Celsius is the same increment as 1 Kelvin. Okay? Makes it easy to convert. And when we're measuring temperature, we're measuring that transfer of heat. Okay? Whenever there's a chemical or physical change, there has to be some kind of energy transfer. Sometimes that's in the form of heat. Usually it's in the form of heat. Let's talk about absolute zero. This is in Kelvin. So absolute zero is 0 degrees Kelvin. We haven't been able to get matter this cold, but if we were, it's said to be the moment or the temperature when all particle motion would stop. Okay, that means solid, liquid, gas, doesn't matter. It would all stop, smaller and tighter and not moving at all. Solids vibrate, liquids move around, and gases can go all over. When we're converting between Kelvin and Celsius, really nice and simple. If you started in Celsius, you just add 273 and you have it into Kelvin. So 0 degrees Celsius plus 273 gives you 273 Kelvin. Okay, opposite way, if you're in Kelvin and you want to go back to Celsius, subtract 273. There's no negatives in Kelvin. Okay, 0 Kelvin is absolute zero. That's another nice reason that scientists like to do it. Don't have to worry about negatives. In this video again, please feel free to pause. If I'm going too fast, you can jot it down. But let's move on to heat. Okay, again, we're measuring heat transfer. We're talking about temperature, but we do have another unit for heat, measuring actual heat. And again, energy can be in transit between two systems. We can measure the difference in heat, that's temperature. Measuring heat itself, okay, transfer of heat always happens naturally from high to low. So if something's really, really hot, it's naturally going to transfer to a lower temperature. The heat's going to escape. Okay. So when we put ice into water, it's not that the ice is cooling down the water. It's that the water in the solution is actually heating up the ice cube, which causes it to melt. It goes from high to low. The liquid is hotter, so that heat's going to move into the ice cube. Unit is joules. Okay, that's our SI unit, international unit. And another common unit is the calorie. We're all used to hearing about calories, and calories are actually how much heat can be produced by that piece of food. Okay, and chemists actually burn in a very controlled way, burn samples of food to figure out how much heat can they give off, and that's how many calories. The conversion for that, 1 calorie is equal to 4.18 joules. The calories on our actual food, that is a kilocalorie. So 1 calorie with a capital C on your food is equal to 1,000 little calories. Heat cannot be directly measured. We calculate its effect using temperature, but we can measure that difference. Okay, we talk about the joule and the calorie. Again, feel free to pause and write stuff down. Specific gravity, this is an interesting one. It's a comparison of densities, and my husband uses it a lot when he brews. He makes beer at home, and we have to figure out how much alcohol is in his brews. And to do that, you actually take, it's called a hydrometer, and it's like a glass tube, and how deep it sits in your liquid tells you the specific gravity, tells you how much alcohol is in there. And we should have realized, we did our distillation lab, we talked about alcohol. Alcohol is less dense than water. So the density of water is 1, okay? If that tube sinks deeper, then we know there's some alcohol in there. Again, comparison densities. Water is used as the reference, and water is 1 gram per milliliter. It has no units. Here's the equation for it. Okay, we have density of the substance that we're testing, okay, in grams per centimeter cubed. If you remember, centimeters cubed is equal to a milliliter. And then the density of water, which is 1. It has no units because these units are then going to cancel because we're dividing its ratio. And we measure it using a hydrometer. I'll have to bring that in sometime. Measurements. So we're done talking about the different types of, I guess, measurements we're going to take. Now we're going to talk about quality of measurements. All right. And there's a couple different vocab words we got to learn. Types of data. Qualitative, we talked a little bit about that. That would be color, texture, smell, taste. So what do I have around me? I have this rubber band ball, okay? And I could say it has different colors. It's got orange, red, blue. That would be qualitative. I could say it's rubbery, okay? That's a quality associated with what? What about that system? Quantitative, I could take the mass, so it weighs 10 grams, all right? I could figure out its density, all right? I could figure out, I don't know, temperature, anything that's associated with a number would be a quantitative piece of data. Again, measurements are only as reliable as the instruments you use. We never use beakers to take measurements. We always use graduated cylinders. They have more lines, and we're going to talk about certainty. They have more lines than beakers do, so they're better for measurements. And we're going to talk about why. A review, we talked a little bit about accuracy and precision before. Accuracy is the nearness to the known value, but scientists don't always know the known value, so sometimes we have to use precision only. To calculate accuracy, we take experimental minus the accepted value over the accepted value, okay? And we get our experimental error. And we'll be using this equation a ton in lab. Oh, times 100, we want a percent error. Back up, let's talk about precision. Okay, again, concerned with reproducibility. Can you get, sorry, I'm still holding on. Can you get the same numbers over and over? And sometimes that's all scientists have is reproducibility if we don't know the known amount. But if we can keep getting the same thing over and over, we're probably circling the right answer. We had gone through this, poor precision, or good precision, good accuracy. This would be good precision, poor accuracy, and then poor, poor. We went over this before, I'm not gonna do it again. And a note, accuracy depends on the quality of your instrument. So if you're using a beaker versus a graduated cylinder, okay, quality of instrument, where precision is based more on how good of an experimenter are you? Can you do the same procedure the same way each time? Are you introducing more experimental error? Okay. Moving on to uncertainty in our measurements. Okay, we have a graduated cylinder here. Now, hopefully you remember, we always measure from the bottom of the meniscus, and this curvature that water or most solutions take inside of a glass tube like this is called the meniscus. Okay, it has to do with the adhesion, cohesion of water, a slight attraction of the water to the glass. So we always measure from the bottom, okay? And when we look at this, we all might take a different measurement. So I'm going to jump ahead here. The graduations, okay, are the little lines. Now I look at this. I know that for sure the water is 20, 21, so it's for sure 21. And then this is an uncertain digit. It's between graduations, so we're not 100% sure what that number is, okay? Here's an example. If I have 4 different students, they might all take a different measurement. So it'd be 21.4, 0.5, 0.6, 0.7, depending on what that student saw. That's our uncertain digit, okay? So let's define those quickly. Certain digits, in this case, would be 21. That's where we know, that's what the graduation shows us. We know for sure that water is above 21, but it's in between. There's no graduation, so we have to guess. It becomes an estimated or an uncertain digit, okay? The uncertain digit is the third one in this case because it's uncertain. It's different for each student, and it's the one that we had to estimate, okay? It's always good to keep that in there. That last digit we always assume is estimated when we're taking measurements. And that's going to be different for each different piece of lab equipment. Depending on the number of graduations or decimal places they give you, like a scale, that's going to be different for each one. But it's important to learn how to take good measurements of that. Keep all the certain digits whenever you're taking measurements and always keep the first uncertain digit. We're going to do an example. So this is a burette. All right, we'll use burettes. It goes backwards, so it actually measures how much you've delivered. And I have a picture here. It shows how much you've delivered. So you turn this little knob and the liquid drips out. So this is how much you delivered. So we're actually going to be looking at the 39. We know we've delivered past 39 milliliters. Okay, and this has better graduations than the graduated cylinder did because we're at 39 and we're at 40. So that means that each line is 0.1. So 39.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, okay? So what I want you to do is pause the video and take a look at this. What would you write down for this? Okay, what number would you take down? So pause it now, and I'm gonna keep going. So 39, hopefully you have a guess. 39, I know it's for sure past 39.1. It's past 39.2. And again, we always go the bottom of the meniscus. So right here I can see, I would guess 39.243. So 39.24, sure. Something along there, but 2 decimal places. We need 2 decimal places because that's an uncertain digit. All right. Again, our measurements are only as accurate as the instrument we use. So we got 2 decimal places out of this burette. The graduated cylinder only gave us 1 decimal place. So the more accurate, the more precise your lab equipment, the better. Well, and precision is based on how good are you at measuring. In all measurements, there's a degree of uncertainty. We're human, there's always going to be a degree of uncertainty. We use significant figures to express these. So we're going to talk about significant figures. You're probably not going to like them. They are a little bit challenging, but they're so important to chemistry and to taking good measurements. Before we get into that though, we're going to review scientific notation. Okay, this is used to express really, really big or really, really small numbers. If you remember, let me catch up on my paper version here. We use a coefficient and we raise it to an exponent, to a power of 10. So it's just moving the decimal place. So here's my example. When we have this number, is called your coefficient. Okay, this should be between 1 and 9.99. I know sometimes you see it like 25, like 2 numbers, like 10 point whatever, and change the decimal point. We don't want that. Sorry, I'm jumping ahead. So if the exponent is positive, that means the number is going to be getting bigger, and you move the decimal to the right. So we'd move the decimal to the right 4 times. So if we 1, 2, 3, 4, so it's 25,000. Here then, a really, really small number like this, 1.0 times 10 to the negative 16th, that means if it's negative, it's going to be moving to the left. The number is getting smaller. And as you can see, we moved this decimal, which would have been right over here, 16 places. Okay, it's much easier to write this than this. Review, a lot of times you're just going to plug them into your calculator. So you may not worry about this as much, but we should go over how to multiply them. To multiply these numbers, you can multiply the coefficients and add the exponents. So for some reason, if you don't have a calculator, you're not sure, you can always check it this way. So here we have an example. You can take a look. We multiplied the 4 and the 2.3 to get 9.2, and then we added the exponents, which gives us 7. So that's multiplying. To divide them, you divide the coefficients, and then you subtract the exponents. Here's another example. You can write this down, and we're going to keep moving. To add or subtract, you have to align the decimals. It has to be in the same exponent. Okay. Here's my example. This is 5.4 times 10 to the 4th plus 2.1 times 10 to the 3rd. So we have to get it into the same exponent. So I'm going to move that decimal 1 place over to make it 0.24 times 10 to the 4th. Line them up and add. The exponent then is going to stay the same. Again, most of the time you're going to be putting these into your calculators. The ones we have look a lot like this, and we use the EE button to do this. I'm going to go over this with you in class. If you know how to use, a lot of you use the caret button, this one, okay? If you know how to, great. Otherwise, when I come back, we'll talk about this and make sure everyone knows how to use this in your calculator. All right, significant figures. I'm going to wait on this, okay? This is one that does challenge students, and I want to do it with you. So this is where we're going to pick up next time in class, hopefully not online. So thank you for watching this video. Again, as you watch, please stop, pause. Let me know if you have any questions, and I will see you all back on Monday. All right, thanks, guys.